Hello and welcome to MyScience Tutorials. In today's video, we want to look at a resistor-capacitor series AC circuit, or what we simply call RNC series AC circuit. Now, before we begin, if you're new to MyScience Tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. So what do we mean by a resistor capacitor in series AC circuit, or what is an RNC series AC circuit? So in this type of series AC circuit, we have our major component to be a capacitor and a resistor connected to a source of an alternating current. So if we draw the circuit diagram for this particular RNC series AC circuit, we are going to have our resistor connected to a capacitor, which is then connected to an AC source. So this is our AC source. Okay, so this is our resistor, this is our capacitor. Now the current flowing through this entire circuit is over here as I. Now there is a potential difference, or different potential difference goes across each of the various components that we have over here. That is the resistor and then the capacitor. So the potential difference across the resistor over here is what we call the resistive voltage, denoted by VR. And then the potential difference across the capacitor is what we are calling the capacitive voltage, VC, over here. Now, if we do something we call phasor sum of VR and VC. If we do a phasor sum of VR and VC, we are going to get the overall voltage across this entire circuit, which we are calling the applied voltage, V. Now, in this type of circuit, the current we have over here leads the applied voltage by an angle between 0 to 90 degrees. So for us to illustrate what we mean by the current leads the voltage or the applied voltage by an angle between 0 to 90 degrees, we need to look at something we call the phasor diagram. The phasor diagram. So the phasor diagram for this type of circuit is like this. So we are saying the current is leading the current is leading the voltage by an angle between 0 to 90 degrees. So we have this over here, we have our current is over here, then we have, let's say from here to here is our resistive voltage, so we have VR, and then from all the way from here down here is our capacitive voltage. Now if we extend this a little bit down over here, the distance from here to here, which is the resultant of VR and VC over here, is what we are calling our applied voltage, or V. All right, so the angle now between the the current through the entire circuit over here and the applied voltage is what we are calling the phasor angle, or the phase angle. So this angle can range between 0 degrees to 90 degrees, as you can see in this diagram over here. So from the phasor diagram we have over here, we can deduce two types of triangles over here. We have one we call the voltage triangle, and we have the second one we call the impedance triangle. So let's look at the voltage triangle and then the parameters that we can obtain from the voltage triangle. So we have the voltage triangle. The voltage triangle is just, we are taking the VR and then the VC over here, and then the resultant over here, which we are calling the applied voltage. So it looks something like this. Okay, so over here we have our VR, which is our resistive voltage, which is given to us by IR, current multiplied by resistance. Then we have our VC over here, which is I multiplied by capacitive reactance, XC. And then we have our V, which is our resultant over here, is equal to I multiplied by Z. The Z over here is what we call the impedance, which is the overall resistance to the flow of current in this entire RNC circuit. Okay, so the angle over here, as we can see from the top over here, is what we are calling the phase angle, and then over here is 90 degrees. So this is the voltage triangle. The second one is what we call the impedance triangle. Now the impedance triangle is also the same as the voltage triangle. The only difference over here is, instead of writing the respective voltages over here, we just write the respective oppositions to the flow of current. So it's going to be like this. This is 90 degrees. This is our phase angle. And over here, we are going to have our resistance, okay, which is the oppositions to the flow of current in a direct current way. Then we have our VC, opposition to the flow of current in an AC circuit containing just a capacitor, is what we are calling the capacitive reactance. So we have XC over here. And then the opposition to the flow of current in this entire circuit is what I said we call the impedance, so Z over here. Okay, so let's look at some of the parameters or some of the things that we can find from this voltage triangle and the impedance triangle. Now, if you want to find the voltage over here, which is the applied voltage, we need to use the Pythagoras theorem. So using the Pythagoras theorem, we know that the resultant, which is the longest, or the hypotenuse over here, the resultant square, V squared, will be equal to the adjacent and then the opposite square, the sum of those. So we have VR squared plus VC squared. So if we make V the subject, we are going to get the root of VR squared plus VC squared. So this is what we are calling the phasor sum of VR and VC, because we can see we are adding VR and VC, either this or this. So the phasor sum of VR and VC is what we are calling the applied voltage, and this is how we do the phasor sum. So this is how we find the applied voltage in this given scenario. Now, for us to find the angle over here, which is the phasor angle that we have over here, we can see that from this particular triangle, we will be given resistance, or the VR, will be given VC, but we do not know the V, which is the applied potential difference or applied voltage. That is how come we found that first. So for us to find this angle, we have over here, this is the opposite side, and then this is the adjacent. So the trigonometric ratio that gives us opposite and adjacent is 2r, which is tan. So we have over here tan the phase angle will be equal to the opposite, which is VC over here, will be at the top. So we have VC over VR over here, will not be at the base, VR over here. So this is how we find the phase angle if we use the voltage triangle. So this equation, equation number 1, this equation, equation number 2, they are very, very important equations that we need to use and we need to keep in mind. Now, if we look at the impedance triangle over here, let me use another color. If we look at the impedance triangle we have over here, if we want to find the impedance over here, it's going to be the same as how we find the applied voltage over here. Because this is the hypotenuse, we're going to have Z squared will be equal to R squared over here plus XC squared. So the impedance Z will now be equal to the root of the resistance squared plus XC squared over here. So this is equation 3, another very, very important equation that we need to keep in mind when we are solving problems related to RNC series AC circuit. From this triangle as well, the impedance triangle, we can find the phasor angle over here. So again, this is our opposite, this is our adjacent. So it means that if we want to find the phase angle over here, it is going to be tan alpha, or the tan phasor angle, is equal to XC, which is the opposite, or the capacitive reactance, over R, which is the resistance of the resistor in the circuit. So this is equation number 4. So equation number 1, that is how to find the applied potential difference or the applied voltage. Equation number 2, how to find the phase angle when you have the when you have the capacitive voltage and then the resistive voltage. Equation number 3, how to find the impedance or the overall opposition to the flow of current in this circuit. And then equation number 4, which is something similar to equation number 2, that is how to find the phase angle when you have the capacitive reactance and then the resistance of the resistor in your equation. So these 4 equations are very, very important, and let's keep them in mind. So now that we've gone through the basics of RNC series AC circuit, and we've looked at all the important equations that we need to note, let's proceed to have a look at some few examples to really appreciate what we are doing over here. So the first question we want to try our hands on is problem number 1. We have a resistor of 25 ohms is connected in series, this is very important, in series, not in parallel, in series, with a capacitor of 45 microfarad. We are to calculate A, the impedance, and B, the current taken from a 240 volt 50 hertz supply. Find also the phase angle between the supply voltage and the current. This is very easy and very straightforward question to do. So let's write down our solution. Now, the first thing I want to do is to write all the parameters that I have and those that I don't have. That way I know where to start and where to end. So I have a resistor of resistance 25 ohms. So R is equal to 25 ohms. And I was told it is connected in series to a capacitor which has a capacitance of 45 microfarad. So I was told to calculate the impedance, the current, if I have a voltage or the applied voltage of 240 volts and then a frequency of 50 hertz. Right, this is beautiful. Let me try and draw the circuit diagram for this particular question. So let's draw the circuit diagram so that you can understand what is going on. The circuit diagram. Okay, so the circuit diagram is going to look like this. I have my resistor over here, and then I have my capacitor connected to it in series, and then I have my AC source over here. Okay, so my current is over here, I don't know. My applied voltage is 240 volts and the frequency of 50 hertz. My capacitance C is 45 microfarad. My resistor has a resistance of 25 ohms. Then we have our VR over here. And then we have our VC over here. Okay, so this is our circuit diagram for this particular example. So the first thing we've been asked to find is to find the impedance. So A, impedance. We know that impedance is the total opposition to the flow of current in this RNC series AC circuit. So from the previous explanation that I gave, I said the impedance is equal to the root of R squared plus XC squared. Now we have R, which is the resistance we have over here, but we don't know XC, which is the capacitive reactance. Now the capacitive reactance of a capacitor is given by the formula 1 over 2 pi Fc, where F is the frequency of the circuit and then C is the capacitance of the capacitor. So let's have a look at that. So this is going to be, we have 1 over 2 pi, our frequency is 50 hertz, multiplied by the capacitance of the capacitor, which is 45 microfarad. So 45 times 10 raised to the power minus 6 over here. Now, if we compute everything we have over here into our calculator, 1 over 2 pi multiplied by 50 multiplied by 45 times 10 raised to the power negative 6 is going to give me 70.74 ohms as my capacitive reactance. Now that I have my capacitive reactance, I can go ahead and find my impedance. So Z which is my impedance, is going to be the root of my resistance is 25 squared plus my capacitive reactance is 70.74. I also squared that as well. So if I compute everything over here into my calculator, 25 squared plus 70.74 squared, the root of that answer, will give me 75.03 ohms as the opposition to the flow of the current in this entire circuit, or as the impedance over here. So now that we found the impedance, let's go ahead and tackle the B aspect of this question. Let me do it at the top here. The B is saying we should find the current taken from this particular circuit. So we know that voltage is equal to current multiplied by the impedance. The applied voltage is equal to current multiplied by the impedance. So if we want to find our current, which is I, we need to divide both sides by Z, or the impedance. We are going to have voltage, applied voltage, over the impedance. That will give us our current. So therefore, our current is equal to, our applied voltage has been given to us to be 240 volts over here. We just found our impedance over here to be 75.03. So we have 75.03. If we compute 240 on 75.03, we are going to get 3.20 amperes as our current flowing through this particular circuit. Now, we've also been tasked to find the phase angle between the voltage and the current. So that is easy. Let me use that as C. So we said that tan the phase angle will be equal to VC over VR, or it's also equal to XC over R. Now, if we look at what we have over here, we know that we've not been given VC or VR. Even though we can find it, let's not do that. So we can just use XC, which is the capacitive reactance, which is what we found over here, and then the resistance of the resistor, which is given to us as 25 over here. So we have tan phase angle is equal to, our XC is 70.74 divided by 25 as the resistance for rest. So to find alpha, or the phase angle, we take the tan inverse of our ratio 70.74 all on 25. And if we do that, it is going to give us the phase angle will be equal to 70.54 degrees. So this is our phase angle. Our phase angle is 70.54. Alright, let's have a look at another example to further enhance our understanding of this R and C series AC circuit. So let's look at problem number 2. We have a capacitor C is connected in series with a 40 ohm resistor across a supply of frequency 60 Hz. A current of 3 amperes flows and the circuit impedance is 50 ohms. We are to calculate I, the value of the capacitance C, B, the supply voltage, C, the phase angle between the supply voltage and the current, and D, the potential difference across the resistor, and E, the potential difference across the capacitor. We are also to draw the phasor diagram for this particular segment. So let's go ahead and look at how to tackle this problem. So let's write down our solution. Okay, so we have a capacitor connected in series with a 40 ohm resistor. So we have our resistance is 40 ohms, and then we have our frequency to be 60 Hz. We have a current which is 3 amperes, and then the impedance of the entire circuit we've been told is 50 ohms, which is what we have over here. Now we have to calculate the value of the capacitance C. Alright, so let's look at how we find that over here. So we know, or we've been given from the question, that the impedance is equal to 50, but we know that the impedance is equal to the root of R plus xc. And we also know that xc is equal to 1 over 2 pi fc. So the c we want to find, until we get the xc, which is the capacitive reactance, we cannot find that. So this will be on hold. So let's try and find xc over here, and then we can use that to find our capacitance, which is c over here. So we've been given the impedance to be 50. So we have 50 is equal to the root of our resistance is 40. So we have 40 squared. Sorry, this is supposed to be squared plus xc squared. So this is equal to, if we get rid of the root sign, we square both sides. So this cancels the root. We have 50 squared is equal to 40 squared plus xc squared. From there, we move the 40 squared to the other side of the equal to sign. So we have 50 squared minus 40 squared is equal to xc squared over here. All right, so to find this, we take root of this. So xc is now equal to the root of 50 squared minus 40 squared. So xc, which is our capacitive reactance, is going to be equal to the root of 50 squared minus 40 squared will give us 30 ohms as our answer. So now that we have our 30 ohms, we know that xc is equal to 1 over 2 pi fc. So to find c, or if we make c the subject, we are going to have 1 over 2 pi f multiplied by xc. So from there, we can write c is equal to 1 over 2 pi. Our frequency is 60 over here, multiplied by xc, which we just found to be 30 over here. So if we compute everything over here into the calculator, we are going to get our capacitance C to be equal to 88.42 microfarad. So this is the value of our capacitance over here. Now the B is asking us to find the supply voltage. All right, so we know that V is equal to IZ. This is B. But we've been told that the current is 3 amperes, and we found our impedance, or the impedance given to us in the question is 50 ohms. So this is pretty easy. We know V is equal to 3, which is the current, multiplied by 50, which is the impedance. So this will give us 150 volts as our answer over here. Now let's look at C, the phase angle. The phase angle, we know that tan the phase angle will be equal to xc over r. So our phase angle is the tan inverse of xc, which we found earlier on is 30 over here. So we have 30 over the resistance, which was given to us in the question, is 40. So the tan inverse of the ratio 30 is to 40 will give us an angle of 36.87 degrees. Okay, now that we are done from here, let's try and find the potential difference across the resistor, which is VR, and then the potential difference across the capacitor. So let me quickly get some space over here. Okay, now the potential difference across the resistor VR is given to us mathematically as I, which is the current, multiplied by the resistance. So our VR is equal to, our current is 3, and then our resistance is 40 over here. So if we do that, if we multiply this, we are going to get 120 volts as our VR, or the potential difference across the resistor. Now let's go ahead and look at the potential difference across the capacitor VC. VC is given as I multiplied by XC. So it means VC is equal to 3, which is our current, multiplied by our XC, which we found earlier on was 30. So it means VC is equal to 3 multiplied by 30 will give us 90 volts as our capacitive voltage. Now, we found earlier that our applied voltage, or V, for the entire circuit was 150 volts, which we found earlier. So if that is the case, let's try and see whether the phasor sum of VR and then VC will give us 150. We know that V is equal to the root of VR squared plus VC squared. So the root of VR is 120, so we have 120 squared plus 90 squared. Let's compute these into our calculators and see whether we get V to be equal to 150 volts. If we get 150, it means that this is correct and this is also correct. And if we compute this into our calculator, we are going to get 150, which means our potential difference across the resistor VR and then our VC is also correct. Now this is D and this is E. Now let's look at the final one. We have to draw the phasor diagram. Okay, so the phasor diagram F looks like this. Okay, so we have our current over here, which is 3 amperes. Then we have our resistive voltage, which is 120 volts here. We have our capacitive voltage, which is 90 volts also over here. Then we extend this guy a little down here to see where it will meet with this guy, and that will give us our resultant, which we are saying is our voltage or applied voltage, which is equal to 150 volts over there. We also find the phasor angle to be equal to 36.87 degrees. Okay, so this is our phasor angle. So this is the phasor diagram for this particular example. All right, so problem number 3. For the sake of practice, kindly go ahead and try and solve problem number 3. I will give you 3 minutes for that, and once you are done, we can continue. All right, so I assume you've paused the video and you've tried your hands on problem number 3. Now let's have a look at the solution. So we have a voltage of 35 volts is applied across a series circuit. If the voltage across the resistor is 21 volts, find the voltage across the capacitor. All right, so we've been told that the voltage of 35 volts is applied across the series circuit, which means our applied voltage is equal to 35 volts. Okay, we've also been told that the voltage across the resistor VR is equal to 21 volts. So we have to find the voltage across the capacitor, which is VC. We do not know that, but we know very well that the phasor sum of VR and VC will give us our applied potential difference or applied voltage. So we know that our V is equal to the root of VR squared plus VC squared. Okay, so now that we have this and we have to find VC, let's make VC the subject. So we square both sides, so we get rid of the root here. We have V squared is equal to VR squared plus VC squared. So let's make VC the subject. So we leave it here, move the VR to the other side. We have VR squared, V squared minus VR squared is equal to VC squared. So to make VC the subject, we take the root of both sides. So the root of this side, the root of this side. So this cancels this. We have our VC to now be equal to the root of V squared minus VR squared. So we can go ahead and do the substitution. Our voltage over here is 35 squared minus our VR is 21 squared. So our VC, which is the voltage across the capacitor, is equal to 35 squared minus 21 squared, and the root of that answer will give us 28 volts as the voltage across our capacitor. So thank you so much for watching. That is how we solve problems on a resistor capacitor in series in an AC circuit. So thank you so much for watching, and I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at problems involving RC series AC circuit, or problems involving a resistor and a capacitor connected in series in an AC circuit. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. So in our previous tutorial, we'll look at RNC series AC circuit, where we'll look at all the important parameters, all the important formulas that we need to note and use when we are solving problems involving an RNC series AC circuit. Now in this video, we want to look at further questions to further enhance our understanding of this concept. Now, if you've already watched our previous tutorial, then you are good to go. If not, I'll leave a link in the description of this video so that you can go and have access to that video. All right, so let's go ahead and look at the first problem that we have for today. So we have a resistor of 50 ohms is connected in series with a capacitor of 20 microfarad. If a supply of 200 volts, 100 hertz frequency is connected across the arrangement, we are to find the impedance of the circuit, B, the current flowing through the circuit, and C, the phase angle between the voltage and the current. This is very easy. This is pretty straightforward. So let's go ahead and write down our solution. Okay, so we have a resistor that has a resistance of 50 ohms given to us in the question, and we've been told it is connected to a capacitor of capacitance 20 microfarad. We also have our applied voltage, or the root mean square voltage, to be 200 volts, and then frequency to be 100 hertz. All right, so let's go ahead and draw the circuit diagram for this particular problem. So we have a resistor here which is connected to a capacitor in series, and then they are both connected to an AC source over here. So this is the flow of current, and then we have the potential difference across the resistor is what we are calling the resistive voltage, and then the potential difference across the capacitor is what we are calling the capacitive voltage. Then we have our voltage given to us to be 200 volts with 100 hertz frequency. Then we have our capacitor having a capacitance of 20 microfarad, and then our resistor have a resistance of 50 ohms. Okay, so the first thing we want to look at is to find the impedance of the circuit. Now, the impedance of an RNC series AC circuit is given to us mathematically as the root of R squared plus XC squared. So for those of you who don't know, R is the resistance of the resistor. So this is the resistance of a resistor. And then XC is what we are calling the capacitive reactance. Now this capacitive reactance is the opposition to the flow of current in a circuit that has a capacitor in it. Now for us to find Z, which is the impedance, we need to first of all find the capacitive reactance, because we do not have that given to us in the question. We have the resistance but not the capacitive reactance. We only have the capacitance of the capacitor. So we say but XC is given to us mathematically as 1 over 2 pi FC. So we have 1 over 2 pi FC. That is the formula for our capacitive reactance. So if we do the substitution, we have 2 pi. Our frequency is 100 hertz, which we can see over here. And then our capacitance of the capacitor is 20 microfarad. So we have 20 times 10 to the power negative 6. Okay, so if we compute everything here into our calculator, our capacitive reactance is going to be equal to 79.58 ohms as our answer. So now that we found that, we can go ahead and find our impedance, which is equal to the root of our resistance is 50 ohms, so we have 50 squared plus 79.58 squared. Now, if we compute everything over here into our calculator, we are going to get the value for the impedance to be 93.98 ohms as our answer for the impedance for this particular entire circuit. Now, the B aspect of the question demands that we find the current flowing through the entire circuit. Now, for this RNC series AC circuit, the voltage is equal to the current multiplied by the impedance, which we said the impedance is the opposition to the flow of current in this particular circuit. Now, we've been given the voltage to be 200 is equal to the current we do not know, but we just found our impedance to be 93.98. So if we divide both sides by 93.98, we are going to get the value of our current I to be equal to 200 on 93.98 is going to give us 2.13 amperes as the value of our current flowing through this entire circuit over here. Okay, so the last thing we want to look at is to find the phase angle between the voltage and the current. So to find the phase angle, which is the angle between the current and the voltage, it is given to us as tan the phase angle is equal to the capacitive reactance over the resistor. So over the resistance, so we have our angle is equal to the tan inverse, sorry, let me clean that. So we have the tan inverse of our XC, which is our capacitive reactance, is what we have over here, 79.58, on our resistance is 50 ohms, so we have 50 ohms over here. Now, if we find the tan inverse of that ratio, which is 79.58 on 50, we are going to get an angle of 57.86 degrees as our answer. So this is how we solve this particular problem. Now let's have a look at another example. Problem number 2. We have an alternating voltage V, which is equal to 250 sine 800t volts, is applied across a series circuit containing 30 ohm resistor and 50 microfarad capacitor. We are to calculate A, the circuit impedance, B, the current flowing, C, the potential difference across the resistor, D, potential difference across the capacitor, and E, the phase angle between the voltage and the current. So let's go ahead and look at how we solve this particular problem. Now, solution. So we have an alternating current with voltage. The voltage has been given to us to be 250 sine 800t. Now, this voltage is given to us in a wave form. Now, when we are given the voltage in a waveform, the actual form that this waveform of a voltage is written is V is equal to V naught sine 2 pi ft over here. So if we compare this and then the original form, we can see that our V naught is equal to the 250 over here, and then our 2 pi f is equal to, because we have t here, it means the 2 pi f is equal to the 800 over here. So those are the information that we can obtain from this particular voltage given in a waveform. Now note the 250 volt over here, this is in volt, this is in radians per second. Now remember, the voltage over here, the V naught, is not the voltage that we need to use in an alternating current. We need what we call the root mean square voltage, or the applied voltage, which we are going to look at how we can derive that. So for now, let's have the other parameters that we have in this question. So we have a resistor of resistance 30 ohms. So we have a resistor having 30 ohms, and then we have a capacitor with capacitance 50 microfarad. Okay, so let's go ahead and look at the first aspect of this question, I or A. We are to calculate the circuit impedance. So the impedance Z is equal to the root of R squared plus XC squared. As usual, or as we saw in the previous example, XC is equal to 1 over 2 pi FC, which is equal to 1 over our 2 pi F is 800, which we can see over here, multiplied by the C, which is the capacitance of the capacitor, that is 50 times 10 raised to the power minus 6. Okay, so if we multiply all that, we are going to get our capacitive reactance to be equal to 25 ohms over here. So now that we have that, we can go ahead and do the substitution into this formula over here. Let's say that is equation 1. So if we substitute this into equation 1, we are going to get our resistance is 30 ohms. So we have 30 squared plus 25 squared over here. So our impedance is equal to the root of 30 squared plus 25 squared is equal to 39.05 ohms. So that is the answer for our impedance for the circuit. So let's look at B, the current flowing through the circuit. Now we know that the root mean square voltage or the applied voltage is equal to IZ. Now we don't know current, which is what we've been asked to find. We found the impedance, which is what we have over here, but we do not know the voltage or the applied voltage that we need to use over here. We only have something we call the V0 or the peak voltage. Now to find the root mean square voltage or this voltage over here, this voltage, okay, either this or this, is given to us as V0 multiplied by 0.707. Sorry, let me clean that and write it well. So let me clean everything here and rewrite that to be much more clearer. So we are saying our voltage is equal to 0.707 multiplied by V0. So that will be equal to 0.707 multiplied by our V0 is 250 volts. So if we multiply all that we have, we are going to get our applied voltage across this circuit to be 176.75 volts, 5 volts as the voltage for our entire circuit. Now using that voltage, we can now find our current over here. So if we make current the subject, we are going to have our voltage over the impedance, which is equal to our voltage we found to be 176.75 divided by the impedance, which we found earlier was 39.05. So if we divide everything we have over here, we are going to get our current to be 4.53 amperes as our answer for the current. Now the C is saying we should find the potential difference across the resistor. So that is VR, potential difference across the resistor. It is given to us by or as IR, where I is our current, which we just found to be 4.53, and then R is the resistance of the resistor, which is 30 ohms over here. So we have 4.53 multiplied by 30 over here. Okay, so if we compute that into our calculator, 4.53 multiplied by 30 will give us 135.9 volts. Okay, so the D aspect of the question says we should find the potential difference across the capacitor, VC. VC is equal to IXC, where the XC we found to be what? 25 ohms over here at the top. So here is also going to be 4.53 multiplied by 25. And if we multiply these two, we are going to get 113.25 volts as our capacitive voltage. Alright, so the last thing we want to look at, which is the E, is to find the phase angle between the voltage and the current. So let's do that in another color. So to find the phase angle between the voltage and the current, it is given as tan the phase angle is equal to XC over R or VC over VR. Any of this ratio can give you the answer that you want. Because we have VR, we have VC here, we can use these guys. Or because we have XC over here and then the resistance given to us, we can also use that as well. So I will be using this guy, XC over R. So my angle is now equal to the tan inverse of XC, the capacitive reactance, is 25 over the resistance of the resistor, which is 30 over here. So my angle or the phase angle is equal to the tan inverse of this ratio will give me the angle 39.81 degrees. Okay, so this is my phase angle for this particular problem. Now let's have a look at one more final example. Now quickly pause the video and attempt to solve this problem on your own, and let's see what you get as your answer. Once you are done, you can start playing this video and look at the solution that I will provide. Okay, so I believe you are now done, and so let's go ahead and look at the solution that you found for this problem. So we have solution. We have a 400 ohms resistor is connected in series with a 2358 picofarad capacitor across a 12 volt AC supply. We have to determine the supply frequency if the current flowing through the circuit is 24 milliamperes. This is very good. So let's look at the parameters that we have. We have our resistance of 400 ohms. Sorry, the unit is not here. Then we have connected to a capacitor with capacitance of 2358 picofarad. Then we have our voltage is 12 volts, and then we've been asked to find a frequency, which we do not know, but we also know that the current flowing through this entire circuit is 24 milliamperes. So that is very good news. Now for us to find the frequency, we first of all need to find what we are calling the impedance through a circuit, because we have voltage is equal to current multiplied by the impedance. Now we have voltage, we have the current, we can find the impedance. After finding the impedance, then we can go ahead to find our capacitive reactance, which will then enable us to find the frequency that we are looking for. So if we use that approach, we are going to have 12 volts over here is equal to the current is 24. So we have 24 times 10 raised to the power negative 3 multiplied by our impedance. So we divide both sides by 24 times 10 raised to the power minus 3 over here, 24 times 10 to the power negative 3. So we have our impedance to be equal to 12 on 24 times 10 raised to the power negative 3 will give us 500 ohms as our impedance for this particular circuit. Now that we have the impedance, we know that impedance is equal to the root of R squared plus capacitive reactance squared. So we know that Z squared minus R squared will give us XC squared. And so the root of Z squared minus R squared will give us our capacitive reactance, which is what we are looking for. So if we do the substitution, we have our impedance is 500. So we have 500 squared minus our resistance is 400, so we have 400 squared to be equal to capacitive reactance. So our capacitive reactance will now be equal to the root of 500 squared minus 400 squared will give us 300 ohms as our capacitive reactance. But also from here, we know that our capacitive reactance is equal to 1 over 2 pi fc. But we are looking for the frequency over here. So if we make the frequency the subject, we interchange the position of the frequency and then the xc over here. So we have our frequency will be equal to 1 over 2 pi c multiplied by xc. So it means our frequency is equal to 1 over 2 pi. Our capacitance is 2358. Pico is times 10 raised to the power negative 12. Then multiplied by our capacitive reactance, which is 300 over here. So using our calculator to compute this entire ratio that we have over here, we are going to get our answer to be equal to, let me write it at the top over here. So our frequency is going to be equal to 225 times 10 raised to the power 3 hertz. Okay, so which we can rewrite as 225 kilohertz as our final answer. So this is the frequency of the entire circuit. So thank you so much for watching. This is how we solve problems on RNC series AC circuit. I hope this video has been very helpful to you to really appreciate how to maneuver your way around problems that has a resistor and a capacitor connected in series with an AC source as their voltage supply. So thank you once again for watching, and I will see you in the next video. Bye bye.